Before I get into this video, I'd like to start by making two important announcements. Firstly, the video featuring an
interesting discussion about Donald Trump
will certainly be released in the next month. Second, and most important of all, I have finally decided on the topic of my new upcoming film. I've put 3 graphics on the homepage of my updated website, which you can have a look at to try and have a guess about what my new film will be about. I'm assuming that you're having a look at those 3 graphics right now, and once you have done that, please answer that question right there so that you can let me know. Now that I've announced the 3 important things I was going to announce, let's get straight into this video. Think back to Year 7 and 8 high school physics. Let me guess, you probably learnt about the basics behind forces. You learnt about gravity, friction, and the normal force. Now, these forces do apply to the macroscopic world, that is, the big world we live in. But down at the quantum scale, we talk about the fundamental forces, not these classical ones, because they don't work. The 4 fundamental forces of nature are the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. And in this tutorial, we're shortly going to be learning about the particles that help carry these fundamental forces. These particles are called bosons, and they're named after the Indian particle physicist Satyendranath Bose. Bosons are the particles by which the influence of fundamental forces is exchanged between fermions. Basically, when a force is applied by one particle to another particle, bosons are exchanged between the 2 particles that allow the exchange of that particular force. Now, the Higgs boson is one boson that we won't be talking about in this tutorial, because this boson is so special that it deserves a video on its own. And that video is not this video. That is for another tutorial. In this video, we're going to be learning about the strong and weak nuclear forces that exist within a nucleus, and how they're exchanged between particles and which particles they can be exchanged with. Let's discuss the strong force first. The strong force is the strongest of all fundamental forces of nature. Moreover, it can be felt by all quarks and hadrons. Hadrons are basically any particles that are made up of a multiple number of quarks. And the strong nuclear force exists in the nucleus, and it keeps the protons and neutrons together. It's called the strong force because it's stronger than the electromagnetic force in the nucleus. Because remember, there are many protons in a nucleus, and protons are positively charged, which means they should be repelling each other. But something keeps them together, and that is the strong nuclear force. And they're exchanged by gluons and mesons. Let's talk about the gluon. The gluon is the boson that allows the exchange of the strong nuclear force. It was theorized by Murray Gell-Mann and has an electric charge of 0 relative to an electron, and has a mass of 0 as well. It's called a gluon because literally it glues things together. It glues protons and neutrons together to form a nucleus. Let's talk about the existence of the strong force in a hadron, in particular the proton. That's a pretty diagram of a proton. So as you can see here, between the 2 up quarks and the 1 down quark, the strong force is being exchanged by gluons. The strong nuclear force makes the quarks stick together and make the proton. The same occurs in any hadron, including a neutron or a pion. The strong force not only exists inside individual hadrons, but it also exists inside a nucleus. As we can see here, the strong force is exchanged between protons and neutrons, not by gluons, but by mesons. All the protons in a nucleus have a positive charge, but they don't repel each other because they're kept together by the strong force. I've mentioned the word meson quite a few times now. What do I really mean by it? Well, a meson is basically any type of particle consisting of a quark and an antiquark. The general structure of a meson is any of the 6 types of quarks and any of the 6 types of antiquarks. 2 examples of mesons are pions, consisting of 1 up quark and 1 anti-down quark, and kaons, consisting of 1 up quark and 1 anti-strange quark. If you don't know what quarks, leptons or fermions are, just watch my first tutorial of the science of everything, and that should clarify everything for you. Okay, now that we've racked our brains with information about the strong force, let's learn about the weaker side of things, the weak force. The weak force is the second weakest of all fundamental forces. If you want to know what the weakest of all forces is, well, you're gonna have to wait until another tutorial. Also, it can be felt by all fermions, unlike the strong force which can only be felt by quarks. The weak force can be felt by both quarks and leptons. And it doesn't make particles stick together like the strong force does. It does, well, other weird things. It makes particles change types between each other. It's responsible for bizarre particle changes. And it's exchanged by 2 different types of bosons, the W bosons and the Z bosons. Let's talk about the weak force bosons, the W and the Z bosons. These 2 particles were theorized by Sheldon Lee Glashow, Steven Weinberg, and Abdus Salam. The W plus boson has a charge of +1, while the W minus boson has a charge of -1. The Z boson remains neutral. The W bosons have a mass of around 80 gigaelectronvolts per speed of light squared, whereas the mass of a Z boson is around 11 more than that. Remember how I talked about the weak force being responsible for bizarre particle changes? Well, the technical term for those bizarre particle changes is the weak interaction. The weak interaction takes place between the up-type quarks and the down-type quarks, and the charged leptons and the neutrinos. Up-type quarks can transform into down-type quarks and vice versa, and same with the charged leptons, which can transform into neutrinos and vice versa. These transformations take place due to the exchange of W bosons. These particle changes essentially involve a heavier particle transforming into a lighter version of itself. And this is essentially what takes place in the core of a star, like our sun. And what about the Z boson, which we haven't really talked much about? Well, the role of the Z boson is only to exchange energy and leave everything else unchanged. And in a layman's terms, a Z boson is basically a photon but with mass. Now, finally, let's move on to discussing the electromagnetic and gravitational. Hold your horses, that's for the next tutorial. I can't just tell you everything about the fundamental forces in just one video, can I? Even though the series is called The Science of Everything. I can't just overload your brain, because I don't want to do that. That's unhealthy for you. My upcoming videos will be about Donald Trump, how concrete can grow on its own, and what the top 10 most dangerous poisons are on Earth. So if you want to learn about all that interesting stuff, which I'm sure you do, I mean, who doesn't? Please be sure to subscribe, like, share, and comment on this video as well. I'll see you later.